All right, so today we're going to talk about logarithms and exponential models. Now, in Math 108, you would have studied exponential growth and decay and looked at exponential models there. So, and you would have learned there, two different forms for exponential models. One is in the form Q equals, let me get my pen working here. Q equals A b to the t, okay, where a is a constant, b is a constant, and t is something like time, okay. Now, a is the initial value, right? Because if we put in 0 for t, then this becomes b to the 0, and so that means at time t equals 0, the quantity q is a. And so oftentimes instead of a, you'll see q0, which means the q at time 0, or the initial value, the initial quantity. Okay, so t is in time. B is called the growth factor, okay, because it's the factor that we're multiplying each time as time increments, right? So, and R is called the growth rate. Now, sometimes it's called the discrete growth rate, and that's because oftentimes this is used to model discrete growth, like compound interest, where your growth is happening at discrete time increments. Okay, and so when r is greater than 0, we have exponential growth, and when r is less than 0, we have exponential decay. Okay, and so b is 1 plus r. Okay, so all right, so the other model that you probably learned about is this model where E is Euler's constant. Okay, so it's a fixed value, and but again, A is the initial value, because if you put 0 in for t, then you get Q is equal to A, right? Because e to the 0 is 1, so you just got A times 1. So the initial value is A, and also sometimes called Q0. E to the k is the growth factor. So it's the same growth factor as we have over here in this other equation. The growth factor B is the same as e to the k, where k is some constant. And k is called the continuous growth rate. So when k is greater than 0, you have exponential growth, and when k is less than 0, you have exponential decay. All right, so both of these are actually continuous functions, okay? It's just that sometimes this equation here on the left is often used to model discrete growth, like compound interest, and so sometimes it's considered in particular, this growth rate is considered a discrete growth rate, but it's still a continuous model. So it's a continuous function. Also, we can rewrite this. We can, if we want to know what R is, we can always take R and subtract 1 from B. So, oops. So we can get that equation. Also, over here, because e to the k is equal to b, then k is equal to the natural log of b. Okay, if we just take the natural log of both sides. All right, so the first thing we're going to do in this first example is convert from one form to another. In this case, we're given exponential models in the e to the kt form, and we want to convert it to the other model where we have q equals a times 1 plus r to the t, or a b to the t, either way. So let's see how we do this. Well, all right, so what we have here, if we want to convert this to the other model, let me just scroll up so we can actually see. Can we get both of them on there? Okay, so there's our two models. I think that'll be good. So we can actually rewrite this as 6e to the minus 0.04 to the t, right? Just using the rules of exponents, right? And then you can see that we can then, this e to the minus 0.04 is just a constant. So we can calculate what that is. So we get 6 And then if we put this into our calculator, e to the minus 0.04, we get 0.9608. And then we still have the power of t. Okay, so now you can see it's in that form. Q equals a b to the t. Now if we want it in the 1 plus form, we could actually rewrite it as 6 times 1, and in this case it's basically minus 0.0392. Okay, that would give us the 0.96. So you can see we have decay in this case, and that's all to the t. All right, so in this case our r is negative. All right, so, and we're asked to find the initial value a. Well, that's easy enough. A is just 6. R is equal to 1 minus, or b minus 1, and which we found here. R is just minus 0.0392. And then our k value, we can just read off of the original equation. It's minus 0.04. Okay. So if they ask for growth rate, it's r. Continuous growth rate is k. So there's another one. That's part B here. So I'm going to suggest that you pause the video here and give it a try on your own, and then restart it, and I'll go through it with you in case you need, or if you want to check your answer. All right, so let's do the same thing with this one. We have 12 e to the 0.09. I'm going to put that in parentheses to the t. Okay, it's the same equation, but now we can calculate that constant, e to the k. And so we end up with 12 times 1.0942 when I put that on my calculator to the t. So you can see then we have 12 times 1 plus 0.0942 to the t if we want it in this form that we're asked for. So this, we could actually write this as q equals, like I said, I didn't do that over here, but that gives us the form that we're asked for. All right, so what's a? What's the initial value? Well, that's 12. R is, we can just read it right off of the equation. We've got 0.0942. Okay. And then our k value, we can just go back up to the original equation, and so our k value is 0.09. All right, so I will meet you in the next video.